Yeah, welcome back to the second part of the morning session. It's really a great pleasure to have Katharina Schratz here, Münster, and she did her PhD. But is really allowed to say there's C grant, one of the recognition work. Very much.
Thank you very much. Thank you very much for the invitation. It's a great pleasure to be here in Münster. And so I want to talk about resonances as a computational tool, and this is a novel numerical integration technique I was working on in the last couple of years. And as you see, I don't have a lot of slides, and the community is very versatile, so please do not hesitate if you have any questions, or even better, any suggestions during my talk. Okay, and so what is the motivation? So what did get me interested in the subject? What I think we understand very well nowadays in numerical analysis or computational mathematics as smooth solutions. So for instance, if you think about the Schrödinger equation with a smooth initial data, the solution stays smooth at least a certain amount of time, and you can easily approximate it numerically. So basically, you can use any decent numerical method, and you get a good approximation to the solution. This, however, drastically changes when we look at rough data. So for instance, here we see a numerical simulation of the so-called Talbot effect. So this is some nonlinear dispersive quantization. And what happens is the following. You have a step function initial value, and you solve the cubic Schrödinger equation, and you look what happens as time evolves. And very interestingly, mathematically and physically, what you observe is that the solution quantizes. So at certain, as you look at the time evolves in the solution, and at certain time points, the solution quantizes. And this is, of course, very nice numerically, because you know analytically that your solution has this quantization. So you can test your numerical scheme and see in how far you reproduce this quantization on the discrete level. And here we see quite drastically how classical methods fail. So in blue, we see the exact solution. So we see the solution of the Schrödinger equation at some time point where you have this quantization. And in red, we see the numerical simulation with a strength splitting method. So if you never heard of strength splitting method, don't worry, I will explain it in a moment what it is. But it is one of the most famous methods to solve Schrödinger equations numerically. And what we see is that this strength splitting method completely fails to reproduce this pattern in the exact solution. Okay, it does not reproduce at all the structure of the solution, and this is the problem because the solution is rough. And splitting methods, as most classical methods, work very well if you're smooth, if you see infinity. However, once you turn to rough data, rough solutions, they drastically break down. And this is much more a problem for dispersive equations, such as the Schrödinger equation, because unlike for parabolic problems, we do not have this smoothing property. So basically, if you start rough, you stay rough. And this somehow got me interested. How can we design, or in how far can we actually design numerical methods which also work for rough data? And in the next 40 minutes, I want to give you an idea I had on how to design new numerical methods, which have the intention to really embed the underlying structure of the PDE, also rough solutions, into the discretization. Okay, and to explain my idea, let us look at one concrete, very fundamental but simple model problem, the called the Weg de Vries equation, which is a model for shallow water waves. And mathematically, this is described by the following PDE. So we have the time evolution of the solution driven by the third order differential operator dx cubed, and then we have a Burger's nonlinearity dxu squared. Now, before I give the idea of my resonance technique to attack this problem and to design numerical schemes, let me first give an overview on classical numerical methods, how to solve this KdV equation. Because in order to have the idea for the new methods, we first have to understand why and when do classical numerical methods fail. And so one of the most used methods for the KdV equations are splitting methods. So the basic idea of splitting methods is the following. You have a complicated PDE, you take this complicated PDE, you split it into a series of simpler subproblems, solve these simpler subproblems, compose their flows, and get an approximation to the original solution. So if we look at the KdV equation numerically, we have two main difficulties. We have the third order differential operator, and we have the Burger's nonlinearity. And the simple idea of splitting methods is now the following. Instead of considering the full equation, the full KdV equation, in the first step, we forget about the nonlinear term in our equation, and we simply look at the linear part, dtu plus dx cubed u is 0. And in the second step, we forget about the third order differential operator in our equation, and we only look at the nonlinear part in the KdV equation. Okay, and if we think numerically, if we only think about the time evolution, so we don't for the moment think about spatial discretization. Of course, in the end, we have a PD in time and in space, so we also have to apply some space discretization. But for the moment, if we only think about the time evolution, then we see that indeed we can solve both subproblems exactly. So here we can just directly write down the solution. This is just exponential minus t dx acting on the initial value. And the second problem, S2, we can solve with the method of characteristics exactly. So we took this KdV equation, which is probably for most of you very easy, but numerically not so easy because you have a differential operator and nonlinearity. We split this structure into the two subproblems, linear and nonlinear part, and we can solve both exactly. Now in the end, of course, we do not want to have an approximation to the subproblems. What we want to have an approximation to the exact solution, and this is where the splitting comes into play. So the basic idea is the first order least splitting method. So the idea is the following. We have here somewhere the initial value u naught, okay? And then let us assume that the exact flow takes the initial value and transports it up here. Okay, this will be my exact solution at time tau. So this is basically if I want to solve my PD on the interval 0 to capital T, then what I always have to do in numerical analysis, I have to discretize. Okay, so I discretize. Okay, I use time step tau. And then now what we do is the following. So let us assume that the exact flow takes my initial value and maps it to the exact solution at time tau. The idea of the splitting is now the following. Instead of following the exact flow, I take my initial value and then first I transport it in the direction of the linear flow. So here I solve S1. Then I end up somewhere here, and then I take this as initial value and then I transport it into the direction of the nonlinear flow. So here I solve S2. And then I end up somewhere here, and this will be my numerical approximation U1. Of course, in the end, what we're interested in numerical analysis is in how far do we actually stay close to the exact solution. Okay, and this is the called least splitting method. Then you can symmetrize this method, which is the called strength splitting method, where you do half-step linear, full-step nonlinear, half-step linear again. And as if you already had some courses in numerical analysis, what we always know is that symmetric methods have even order. And so as the strength splitting method is even, it naturally has order 2. Okay. Now, of course, what we want to do in the end is we want to know how good is my approximation. And this is where the global arrow comes into place. What in the end we want to do is we want to take our PDE, solve it on 0 to t. We take the time interval, we discretize it in simpler in equidistant or not equidistant, but for the moment equidistant, so we just discretize with time step tau. And then we want to know if we're somewhere at time point tn, which is m times tau, we want to know how far are we actually away from the exact solution, okay? And so what we have to do is we have to iterate our splitting scheme, okay? It does not make sense to make one big step to end up at capital T because we would introduce a huge error. So what we have to do is we have to iterate our splitting scheme. So we start with the initial value, we apply our splitting, then we end up here, we apply again our splitting and so on until we end up at Tn. And then what we want to have is an error bound on this approximation. So if we want to measure the error between the exact solution at time Tn, which is just n times my time steps tau, so I'm somewhere on my grid, and my numerical approximation obtained with the splitting method. And then what you can show, and surprisingly only quite recently, okay, more than 10 years ago, but quite recently for me, because KdV is such a fundamental, simple model problem, and still for a long time it was an open question how you can actually prove convergence of the strength splitting method for it. So Holden, Carlson, Resrebo, and Tau could show the following global error estimate. They could show that if you look at the error in H1, then you get the second order convergence. This is not surprising. We use a second order method. So what we assume is that we get second order convergence. And what we need in our convergence result, we need quite a lot of smoothness. Okay? So if we measure the error in H1, then we need at least additional boundedness of 5 additional derivatives in our solution. And here there's a difference between PD analysis and numerical analysis, because here what I call global error means that I discretize my time interval and then I iterate my scheme. Okay, so this is the local error, which means the error I do on one time step, and then the global error is if I want to go up to time t, capital T. And now in PDE, global error would maybe suggest that you can go with t to infinity, so that you could really solve your PDE up to infinity. But this is an open question in numerical analysis. because what you see in your convergence estimates is the following. You have a constant C of Tn, and basically this constant depends exponentially on your time Tn. And then you see that even if you only go to Tn is equal 10, so you solve your PD on 0 to T, you get an immense error. Okay, so basically your convergence result is useless. And so what is one big question, which I come on later on in my talk, what can we actually do and what can we say if we really want to solve PDs on long time scale? But for the moment, let us say, okay, I say T is 1, so I only want to solve my PD on the time interval 0 to 1. But what I see with this convergence result is the following. I need a lot of smoothness in the solution. This is also what we saw in the first picture. We see that if we go back, okay, if we apply the strength splitting method in this situation, then we do not get any good approximation to the solution, okay? And this is what you see in the convergence estimate on the right-hand side. We need smoothness for this solution. And the second assumption in this error estimate is that the Burger's equation is solved exactly. So through the splitting, you have linear part and Burger's equation, and you assume that the Burger's equation is solved exactly. Of course, we have a PD in time and in space, so in the end, we also have to apply a spatial discretization. And if we say, okay, in S2 we use a method of characteristics, the problem is that we do not necessarily end up on the grid points anymore once we discretize in space. And then we know that Burger's equation has shocks, so we really have to be careful that we do not trigger with our numerical scheme onto the shock. And up to my knowledge, no fully discrete, so time and spatial discretization approach for splitting methods for the KdV equation is known. Okay, another very classical numerical methods in this to approximate the time dynamics of evolution equations are so-called exponential integrator methods. So the basic idea of exponential integrator methods is the following. Instead of discretizing my PDE, I look at its mild formulation given by Duhamel's formula. Okay, so we know that the exact solution of the KdV equation is described as the KdV flow exponential minus t dx cubed acting on initial value, and then basically we have the integral over the free KdV flow exponential s dx cubed acting on the nonlinearity. And now if we think back that we solve our PD on 0 to t, in numerics we always use a discretization, okay? And so basically I will always look on my Duhamel's formula at the small time interval 0 to tau, okay? And so if I think about my Duhamel's formula on the small interval 0 to tau, then what I can say, and this is the basic concept of exponential integrator methods, is the following. I say, okay, if I just look at my Duhamel integral on the small timescale 0 to tau, then my nonlinearity will not change so much. And so basically I can just freeze it at the initial point where I know the solution, and thanks to this freezing process, I can put it out of the integral. Okay, this is just a simple Taylor series expansion where you freeze the nonlinearity in your integral. And this then already gives a numerical method, okay, because basically what you do, if you just want the first order approximation, you forget the error you do by this approximation, by this freezing, and then you just build your numerical scheme on this approximation, okay, because here you just have the integral over the free KdV flow, but this you can solve exactly, okay. And then what you do to get your numerical scheme, you forget about the local error you introduce, you write down your scheme, so you copy the first term in Duhamel's formula, then you solve the integral over the free KdV flow exactly, which is the so-called phi1 function, and then you just copy your nonlinearity. And again, what you can easily see is what is the local error you produce. So this is always easy to see in numerical analysis what the local error is, because this is just the approximation error you make when you design your numerical scheme. And so here, when we want to see what is our local approximation error, well, basically this is through this freezing process, right? When I take Duhamel's formula and I freeze my nonlinearity. And this is just a Taylor series expansion, okay? So as my remainder, what do I get? I get the term which is of order t square, okay? Because I have an integral, and then I have the Taylor series expansion. Then I get a dx because I have a dx in my equation. This is the Burger's term here. And then I have dtu from Taylor, okay? dtu. And then if I want to know if I take this numerical scheme, what kind of regularity do I need in my solution? Then I just look into my equation and see what is dtu, what is somehow the worst derivative, and then I see this is dx cubed, okay? And then I see, again, also for this exponential integrator method, you need quite a lot of smoothness in your solution, okay? Because you need at least a boundedness of 4 derivatives in order to get a good approximation error. Okay. And so what you need is quite a lot of smoothness, and also in the error analysis, for me at least, this is not very easy, because you really need to use some discrete counterparts of PD techniques, such as Boolean space estimates, if you consider periodic boundary conditions for this model. Okay, and so this somehow got me thinking, why do we need so much smoothness in the solution? Like KDV is such a simple basic model problem, why do classical numerical methods need so much smoothness in the solution? And in order to understand this, we have to first understand the underlying structure of the KDV solution. And if we want to understand the underlying structure of the KDV solution, then again what we do is we turn to Duhamel's formula. And if we want to get just a feeling of the exact solution, we can iterate Duhamel's formula. Okay? So we just iterate Duhamel's formula. So I use that U of S just by the iteration of Duhamel's formula. So I replace T by S. U of S will behave like exponential minus STX cube U naught, and then some higher order integrals, which for the moment I can forget. And then if I iterate Duhamel's formula, what do I see? I see that the underlying structure of the KDV solution is driven by the nonlinear frequency interaction of exponential STX cube and exponential minus S. Okay, this is just an iteration of Duhamel's formula. And now if I want to see in how far my numerical scheme reproduces and stays close to the structure of the PDE solution, I have to see in how far does my numerical scheme embed this nonlinear frequency interaction. And this is where we quite easily see why classical numerical methods fail, because classical numerical methods mostly come from linear ODE theory and then are applied to nonlinear PDEs. And so from a frequency point of view, they linearize all these frequency interactions. So for instance, if we think about the splitting method, what does the splitting method do? It approximates these nonlinear frequency interactions of exponential STX cube and exponential minus STX cube, just as if you would have a linear equation, okay? Because if f, so here we have KDV, so f of u is u square, and if my nonlinearity would be indeed linear, then all these frequency interactions would indeed cancel out. And the splitting method behaves as if you would have a linear nonlinearity, okay? It just neglects all these frequency interactions between the nonlinearity and the differential operator. And the exponential integrator method, on the other hand, swallows all the frequencies within the nonlinearity. And this is somehow also what you see in the construction of the numerical scheme. If we go back to the construction of the splitting method, what do? We have KDV, okay, so we have dx cube and we have a nonlinearity. And what we do is we split the two. Okay, so once we just consider the linear part, we solve dtu plus dx cube u is 0. And once we forget about the linear part and just solve the nonlinear part, okay? And so what happens if now, for instance, okay, I write down the solution, so dtu plus dx cube u0 is 0, and the nonlinear part dtu plus 1/2 dx u square is 0. And now what would happen if in the splitting approach I would change, for instance, the differential operator? So if I would, instead of using a further differential operator, look at the differential operator dx to the power of 5. Then due to the splitting method, in the step where I solve my nonlinear problem, I do not take it all into account what linear operator I have. So if I have, in the step where I solve the nonlinear problem, if I have dx cube or dx5, it would not change at all how I would solve my nonlinear subproblem. And on the other hand, if I would change the nonlinearity in my equation, in the part where I solve the linear subproblem, I would do not take it all the structure of the nonlinearity into account. I would just solve it as before, and not at all change the way I solve my linear part. And this is due to the fact that we really decouple the structure of linear part and nonlinear part. And this destroys the interaction between dx cube and u square. And also in the exponential integrator method, what happens? Okay, what I do is I have this Duhamel's integral, so I have the frequencies exponential STX cube and then my nonlinearity. And what I do is I simply take my nonlinearity and I do brutal Taylor series expansion. So I freeze my nonlinearity at time t0. Okay, and then my numerical scheme takes the frozen nonlinearity and always applies my phi1 function, which is the integral over the KDV flow, to this frozen nonlinearity. But again, if I would change here the power in my nonlinearity, if I would have here u to the power 4, I would just brutally again apply the same phi1 function. I would not change at all how I solve the linear part in my equation. And on the other hand, if I would change the differential operator in my equation, I would not change at all how I freeze my nonlinearity. Okay, and this is also somehow what I always do in these classical numerical methods. I decouple the linear part from the nonlinear part. And this, of course, makes sense for linear equations. For ODEs and in the smooth settings, you also don't have any problem, because this linearization of frequency interactions only runs into troubles once you go to rough data. Because what can you say? For smooth solutions, well, you can just do a simple Taylor series expansion, and this frequency linearized frequency approximation does not introduce a too big error, right? Because you can just do a Taylor series expansion, everything works out. Then there's one thing what you see, what you can prove, and then maybe you can say, okay, maybe I didn't use the best techniques to analyze the numerical schemes. Maybe there's something deeper behind and I did not see it. But then this is the nice thing about numerics. You can just run the simulation and see whether it's true what you thought or whether it's not. And so what we always do, we are interested in so-called convergence plots. So what we see on the x-axis is the time step size. So this is the discretization parameter I use. And on the y-axis, I see the error. Okay? And here I solve the Schrödinger equation with some non-smooth data. And then what, of course, I would like in numerical analysis, I would like to use as large as possible time steps. I would like to discretize as large as possible, because the finer I have to discretize, the more and more computational costs I require. But again, also I want to have a small error, because I want to stay close to the solution. And so basically I would like to be here on the right corner. Okay, so I would like to use large time steps and have a small error. And then what I see, as reference lines, I plot a line with slope 1, okay, and a line of slope 2. And so what I assume is a method has order 1. If it has order 1, the convergence rate should be parallel to the slope 1. And a method that has order 2, the convergence line should be parallel to this line here. And now what I do, I solve Schrödinger with some rough data, with the least splitting and the exponential integrator method, which have first order. So what I would assume is a convergence parallel to this line. And then I also use the strength splitting method, which is a second order method. So I would assume a convergence parallel to this line. And then reality hits. What I see is something completely different. So if I look at the exponential integrator method, which is classically, which means for smooth solutions of order 1, I see that the convergence is very bad. So even if I take a very small discretization, I still introduce a very large error. Okay. And on the other hand, the error of the splitting method oscillates widely. Okay, so if I can be lucky and hit the good step size and have a small error, but I can also be unlucky and hit the bad step size and produce a large error. And this, maybe I was very naive, but what I always thought in numerical analysis is that it always pays off to use higher order methods. Somehow I thought you always gain something if you use higher order. But what you see here, and I think this is very interesting, is that the error of the least splitting method first order and the strength splitting method second order is exactly the same. So you really, for rough data, you do not gain anything in using higher order methods. Okay. And now, what I tried to do was to say, okay, if this classical method struggles so much for rough data, how can we obtain numerical methods which stay close to the exact solution and which have good convergence properties also in the non-smooth setting? And probably you already have the idea, what idea I had in mind. Because basically what we saw is that the problem with these classical methods is that they linearize all these frequency interactions between the differential operator and the nonlinearity. And so the basic idea of this method of resonances as a computational tool is to say we go away from this linearization of frequencies and really try to embed this nonlinear structure into our numerical discretization. Okay, let me explain this a little bit on the KdV equation, where I think I understand it very well, because we have a kind of miracle, at least for me numerically, in these frequency interactions. And then especially let me focus on the open questions, namely as soon as we move away from KdV equation, this gets more and more complicated. So luckily I started this with KdV because here it turns out very nicely, because otherwise probably I would have thrown away the idea immediately. Okay, so what do we want to do? If we want to solve the PDE, we also have to talk about boundary conditions. And for simplicity, let us assume that we have periodic boundary conditions, because once we have periodic boundary conditions, we can explicitly write down how these nonlinear frequency interactions look like. Okay? And so now if we want to stay close to the structure of the solution, one basic idea is to say, instead of discretizing the PDE or using a splitting method, which does not work well, what we do is we iterate Duhamel's formula. Okay, so this is just the first iteration of Duhamel's formula. And then if we want to have a first order method, we can neglect the higher order iterations, okay, because this will just be a term of order tau square, and if we want to have a first order method, we can neglect. Of course, then if we want to produce higher order methods, we have to take more and more of these iterates of Duhamel's formula into account. Okay, and then the only thing we have to do, and this is the only thing we have to understand, is if we have a frequency interaction of this type, in how far can we design the numerical methods which embeds these frequency interactions on a discrete level. Okay, and this is the nice thing if we have periodic boundary conditions, because then we can exactly write down how these frequency interactions look like. Okay, so numerically what we want to do is we want to have a good approximation to this oscillatory integral. And what we don't want to do is we don't want to linearize, because once we linearize, we end up with classical tools and we see that they don't work well if we are at rough data. Okay, and so what we can do, thanks to the periodic boundary conditions, we can write down explicitly how these nonlinear frequency interactions look like. Okay, so we have a quadratic nonlinearity, we expand everything in a Fourier series, we have a VK hat and a VL hat, and then we collect all these nonlinear frequency interactions in our so-called resonance structure, okay, which tells us exactly how these frequencies, how the differential operator and the nonlinearity act together. And so for KdV equation, we get a minus m cubed, so this is the propagator in front of the nonlinearity, then we get a k cube and an L cube, as we have a dx cube and a quadratic nonlinearity. And then somehow for me, the miracle in KdV equation is that these nonlinear frequency interactions really factorize. Okay, so if you look at this nonlinear frequency interactions, you can write this summation as this term k times L times m. And this pays off very well numerically, because in the end, what we want to do numerically, we want to have a numerical scheme which works well for rough data. So we want to stay close to the structure, but we also want to have computational costs at a reasonable level. So we want to have computational costs which are at the level of splitting methods or exponential integrator methods. Because if I design a numerical method which works well for rough data, but then I have to wait 10 years until I have my numerical result, I could also not use it. And so this basically means that what we want in numerical analysis is we want to compute function multiplication in physical space and differentiation in Fourier space, because then with the fast Fourier transform, we can quickly interchange between these two pictures. Because otherwise, of course, you can say, I'm already done. I just know the resonances, I plug them in, I solve the integral, which I can always do exactly, and I have my numerical scheme. For KdV equation, this is indeed true. I just plug my factorization into the resonances, I solve my integral, and I get a very nice compact numerical scheme. Okay, so this is my numerical scheme. The exact structure does not play a role, but what is important numerically is that we can map everything back to physical space. Because in this step where we attack these nonlinear frequency interactions and we move to Fourier space, what we do not want to do is we do not want to stay in Fourier space and carry out all the calculations in Fourier space, because this would be computationally very expensive, right? I mean, here for KdV, this would still be possible. This is a one-dimensional model. We have a quadratic nonlinearity, so numerically this would be still doable. But then if you would go to higher dimensions or to higher order nonlinearities, then your computational effort would just explode, because you cannot just compute all the sums. You would have too many sums to calculate and too many sums to store. Okay, and so this is the idea. Instead of linearizing these frequency interactions, what I really want to do is to embed this nonlinear frequency structure into my numerical discretization. And for KdV equation, this works very well, because we have this factorization, and this allows us to nicely have a good numerical scheme. Now, let us compare this approach of this resonance approach, so where you really iterate Duhamel's formula and then embed this nonlinear structure into your discretization, with the classical method. So let us compare with the splitting method and the exponential integrator method. So what we do with this factorization, we really embed this whole nonlinear resonance structure into our numerical discretization. If we turn to splitting method, what would splitting methods would do? They would, for any number of k and L, just approximate this resonance structure by 0. And this is through this linearization of frequencies. And the exponential integrator method would just approximate all these nonlinear frequency interactions by the first term here and neglect all the other terms in the frequency. Now, let us look at the picture. So this is the idea of this approach. Now let us look at the picture and how far this works well numerically. And so what we know for KdV equations, we have solitone solutions. In solitone solutions, we know the exact solution. We have a certain shape of the solitone solution, and so we can easily test it to see in how far our numerical scheme works. And so what we do, so a solitone solution, you have a certain shape. Then what happens as time evolves, the shape stays the same. It moves to the left or to the right, but the shape does not change. And so what we see here, we see the initial data, and what I compare is the exact solution, which I know, the classical method, the strength splitting method, and this resonance-based approach. And of course, for everybody, I start with the same initial data, otherwise it would be cheating. And then what happens, I see what time evolves. Okay, so I start with the initial data, and then I let time evolve, and I see in how far do my numerical schemes, how do my numerical schemes behave. And then what I see, so in orange, this is the solitary wave solution, this is the exact solution, in blue is the splitting method, and in yellow, this is this new resonance-based approach. And what I see that even at time t is 21, so this is quite short, t is 21 is not very long, but what we see is that the numerical approximation is already very off of the exact solution, and if you would zoom in, you would see that some instability occurs, and if you go on in the splitting method, if you go on in numerical simulation, so you go to up to t is 24, which is again not very long, so these are not long time scales, you see that the classical method, the strength splitting method, even blows up. And this is quite surprising because a solitone solution is C infinity, so you basically cannot have anything nicer than that. Whereas this resonance-based approach quite nicely stays close to the shape of the solitary wave solution. Okay. And now I have 5 more minutes, or? Okay, so. Now, unfortunately, as this worked very well for KdV equations, we thought, okay, why do we not solve all nonlinear PDEs like that? Like, why do we always linearize if we can so nicely just embed this nonlinear structure into our scheme? Why don't we take this to a more general class and design schemes for a large class of dispersive PDEs, but also to other PDEs? Hyperbolic problems and parabolic problems, why don't we take this structure? So the basic idea is, if we have a differential operator and a nonlinearity, what we want to do is we want to design numerical schemes which take this nonlinear interaction of L and F into account. So what we want to go away from this linearization. And so unfortunately, for KdV, we can really solve all of these nonlinear interactions in an explicit way. For other equations, I don't want to say we cannot, because it's just I don't know how to. Maybe someone has an idea how to do it better. I don't see how you can really embed all of these nonlinear frequency interactions in your numerical scheme. Okay, so what my naive idea was to say, okay, if we cannot resolve all of these nonlinear frequency interactions in our method, what do? We take out the dominant part in these frequency interactions, sort of the dominant part exactly, and only approximate the lower order terms. The big question is, of course, what is the dominant part in this frequency interaction? And this is where the resonances come into play, because the underlying structure of resonances exactly tell us what is the bad guy or the bad girl in the system. So what do we really have to take into our numerical discretization? For the moment, what I did is to say, okay, the badness for me is this in the sense of regularity. So what I want to do is I want to solve nonlinear PDEs for rough data. So what I did is to say, okay, I look always at the take the dominant part in the sense of regularity. So which of these frequency interactions are necessary to take into my discretization for rough data? But recently, I moved more to the question, regularity is not everything. If we think back of Schrödinger equations have so much structure. You have energy conservation, you have mass preservation. In how far can you also reproduce this on the numerical level? And so this is an open question where I'm working on right now. In how far can we really find these frequency interactions in the system which are important for structure preservation? And so let me just stop and click a little bit forward. Okay, sorry. And so this, because structure preservation, I think, is a very important concept in numerical analysis. So basically, you have a PDE or a system with a structure, energy conservation, mass conservation. The question is, in how far can you reproduce the structure also on a theoretical level in your numerical scheme? Because you could say if you don't have energy preservation, you're completely off the exact physical relevant solution. And there's one problem in numerical analysis, which are the so-called numerical resonances. So this is a purely discrete artifact which triggers physical energy shift from low to high modes, and this even for C-infinity data. So this sounds very abstract. Let us look at the simulation. What I do, I take cubic Schrödinger equation, I take the same spatial discretization, I take a spectral method, I take the same initial data, and what I plot is the time evolution of the actions. Okay, the actions are preserved in the exact solution, and so I want to see in how far numerical scheme also preserves these actions on the discrete level. I take the same initial value in both simulations, I take the same spatial discretization, I take a splitting method, so I take the same splitting methods in the left and right picture. The only thing that changes is that I change the time step size, so the discretization parameter from the left to the right. In the left picture, which is the so-called non-resonant picture, we see that the actions are nicely preserved over long times. Okay, so here we can really talk about long time, so it's 2,600. I think this is quite large. While as in the right picture, in the resonance setting, we see that this nice preservation of the actions drastically breaks down because we have this energy shift from low modes to high modes. And this, maybe I was also naive, but what I thought in numerical analysis is that always when you discretize finer, you will always get a better approximation. Okay, this is somehow, you think about it if you're in space and or in time, you have your discretization parameter, your time interval or spatial domain, and you somehow think that if you have your solution, you think, of course, the finer you discretize, the better you get to your solution. But then this is, and I think this is why it's so difficult to, in the structure preservation of PDEs, that refining your mesh does not help, okay? Because if you look closer, the resonance step size is actually smaller than the non-resonance step size. So for the larger step size, for the larger discretization, you get a better result than for the smaller one. Okay. And this is even for C-infinity data, okay? And then now let us look to rough data. So now let us go to O of 1 rough data for the NLS equation again, and let us look about the energy conservation. Okay, so the energy is preserved in the exact system, in the Schrödinger equation. The question is what happens numerically? And then maybe you don't see it even, but what is very unfortunately fascinating is that, for instance, the strength splitting method, which is one of the most used methods to solve Schrödinger equations, you even have a blow up in the energy, okay, which is the energy is conserved in your system, but if you simulate it numerically, the energy blows up for rough data. And the rougher the solution becomes, the quicker and quicker your energy will blow up. And then what I'm working on right now is to see in how far we construct numerical methods, which work for rough data and also take the underlying geometric structure into the equation. So let me, sorry to always change. Oops, go back to the setting. So the question is for me, in how far can we go and design numerical schemes which embed the nonlinear structure of the PDE, so you really take this interaction of your differential operator and your nonlinearity into account. You try to take these frequencies which are essential to allow to approximate the PDE for rough data, but also which are the ones which you can take into account, which you do have to take into account to have some geometric properties such as energy preservation or mass preservation or whichever preservation you want. And here maybe, so I have some ideas, but for instance, how you could embed, if you have a symplectic structure in your PDE, how you could embed this in your discretization, for me is an open question. Then another open question is, so what in the schemes you do is you really have to take every equation and design your numerical schemes for each and every equation based on the underlying structure of resonances. What I would be interested, but I have no idea, is to see whether we can use machine learning techniques, because for me somehow it is not a simple problem, but this I think has potential for machine learning applications. You have some frequency interactions in your PDE. Can you find, or can a machine learning technique provide you with the good structure of these frequencies and tell you which ones do you have to take into account to get rough approximations and which ones do you have to get into account to have some structure preservation? Okay, so this is already the end. So what I'm interested in, and what I think is very an open challenge in numerical analysis, is what happens on long time scales. So I think if you go up to T1, we understand well what is working, but then if you go on long time scales, I think it's completely open still what we can do and how far we can actually go. Okay, so if you think about the PDE, there's the questions, once we discretize, in how far can we really go and reproduce this structure on the discrete level. And what I would be interested in is to really see in how far the numerical methods can be used to, for instance, simulate blow-up solutions. Okay, but the problem is if you go and you simulate blow-up solutions, in the end what you see on your computer is a blow-up. But then you have to make sure that you track a blow-up in the PDE and not that you just have an instability as for the splitting method where you know the energy is conserved, but numerically it blows up. Okay, and so this is, so I think there are a lot of open questions, and if you have any idea, I would be happy to discuss further with you.
A lot. And state.
Many thanks for the lecture. You mentioned in several places you said you want to deal with rough initial data. So how rough do you actually have in mind?
So what we can prove, oops, this I just skipped. So what we could prove is to really go down to h sigma sigma arbitrarily small, if we measure the error in L2. For KDV and LS, yes. But again, what we cannot do, what we're working on a moment, this is also, we have error bounds on short time scale, so we can go up to T1, but the question is what happens if we go longer in time? But here what you really have to, so what I think you really have to use, if you want to go down to this level of regularity, you really have to use the PD techniques. For instance, if you think about KDV or Schrödinger equations, also for the PD, if you want to analyze the closeness, you have to use Strichhardt or Bourgain. And I think you really, so this is also what we use. We took these estimates on the continuous level and looked for discretization. But this is somehow not trivial, or at least not for us, because like if you think about a parabolic smoothing property, you have something pointwise in time. So you write down your scheme and then you sum up and you pointwise. And here with the Strichhardt estimates, you're not pointwise in time. So for a long time, we didn't know how to, because numerically you're always discrete, so somehow you have to change it.
May I add another question? So you focus in the analysis of this frequency interaction.
Yes.
So you look at the interaction from a time perspective, but you could also look at the interaction from a space perspective, because you split the fluxes and then the balance between the fluxes is another issue. So my question is, can you translate somehow this frequency interaction into a balance of flux? Is this what you see in the?
It's I didn't think about it in this sense, but it's a very interesting question. Maybe it gives you more insight for the symplecticity or something like that, if you think of it like that.
Yeah, thanks for the very interesting talk. I maybe have one very naive question. So in your analysis for KDV, and I think this also translates to your more general setting, you have these periodic boundary conditions. How dependent is your analysis and your numerics on this condition?
Thanks for this question. So I always present with periodic boundary conditions, and this is also how I started this, because then I can explicitly write down the interaction. So this allows me to understand it better, but then you can generalize this. So what we could do is to really say we have an abstract evolution equation, which can be dispersive, parabolic, whatever. So for instance, we also looked at Navier-Stokes equations, and we have a general domain. And then we can also construct this resonance-based approach in this general setting. And somehow you always win compared to classical methods if your differential operator satisfies some kind of Leibniz rule. But so this is due for Navier-Stokes wave equation, dispersive equations. Thank you very much.
Switch over to the next